Section 2.2, the limit of a function. We're going to dive a bit deeper into what a limit really is, and we'll develop the notation in this section and understand how to describe limits of functions. We're going to start by looking at three separate graphs, or rather three separate functions that are all in the same graph. So I have the function f in this orangey gold color, the function g in this purpley blue color, and the function h in a green color. All three of these functions are undefined at x equals 2. What I mean by that is that we have an open circle along the function at the input value where x is equal to 2. So if we plug x equals 2 into any one of these functions, we get undefined. Essentially, that's because there's a 0 in the denominator. However, even though these three functions have all those undefined points in common, the functions behave very differently around each of the undefined points. Looking at the gold function, we can see that it's a straight line on either side of the undefined point. Looking at the bluish purple function, g, we can see that the function jumps its position on either side of the undefined point. And then looking at the green function, we can see that on the left, the function is shooting up towards infinity. On the right, the function is also shooting up towards infinity. So we've got different behaviors here. We're going to investigate each one of these cases separately in this section. Let's start by looking at the f function. This function is defined by the expression x squared minus 4 divided by x equals 2. And if we zoom in on what happens around x equals 2, we can look at the function values on either side of this undefined point to get a better idea of what's going on here. So let's start by looking from the left. If we were instead of at x equals 2, if we were at x equals 1, follow that up to our function, we're right here at the function output equaling 3. And as we allow that point to move closer and closer and closer to the x equals 2, it feels like our function is going to land on 4 as soon as we get to this open circle. But we know the definition of that function is undefined at the input x equals 2. If you plug 2 into this function, you will get a number on top, 0 on bottom, and that's not okay. We cannot divide by 0. So coming from the left, it looks like we're approaching a function value of 4. Let's take a look at what happens if we come from the right. So instead of being at x equals 2, maybe we're at x equals 3. And if we follow x equals 3 up onto our function, we are at the output that looks like 5. And from that point, if we start to move closer and closer to the x equals 2, right before we get there, it feels like we would land on 4. So again, both sides of this function, if we allow ourselves to slowly inch closer and closer to this undefined point, we feel like we're going towards the function value of 4, even though the function is not defined at the point x equals 2. And so what we say is that as the values of x approach 2, so the values from the left were approaching 2, the values from the right were approaching 2. As those x values were zooming in towards 2, the function values were zooming in towards 4. So as we're shrinking the left and right sides, we're also narrowing in on the vertical, and we're approaching 4. And this is essentially what we use to describe the limit of our function as x approaches 2. If we'd like to get a little more formal in our definition, we can use the definition from the book. Let's break that down for a second. We have f of x is the function that we're talking about, and it's important that this function is defined at all values on the open interval containing the point A. All right, pause for a second. The point A is what we are allowing x to approach. So in our picture, a would be the x value 2. So here we're saying x equals 2. That's the a in this definition. We need this function to be defined everywhere. It could be undefined at the point A, but it needs to be defined everywhere to the left of that, everywhere to the right of that, and it is. We can tell from our picture because there's no other open circles on the graph. Next, we need to imagine a number, L. L is going to be the value that we say the function is approaching. In this picture, that's like the function value 4 that we were looking at in our graph. That is the L in this definition. So this definition says if we allow an x value, some arbitrary x value, to approach A from either side, then the function value needs to be approaching 4. So if I'm following the graph on the left, it's zooming in on 4, and if I'm following the graph from the right, it's zooming in on 4. So what we're saying is that we're letting x get closer to some number a, and the function output, f of x, gets closer and stays close to some value L. And that's exactly, all of that idea is summarized in this small little notation. We read that as the limit where x is approaching a for the function f of x, and we're saying that it's equal to a number L.